All right, hello everybody. We are back for yet another round of statistics for linguists. So welcome, Ling statisticians. Today we're going to talk about covariance and correlation. So kind of moving on from signal detection theory. And I wanted to mention that a lot of these videos have run on the long side of things. I think my power videos wound up being about 2 hours long in total, and my signal detection theory videos wound up being pretty close to that as well, when each of them is supposed to be only 75 minutes ultimately. So today we're just going to keep it short, and I'm getting this up pretty late in the day that it's supposed to be up online anyways. So breathe easy, I guess, for the next however many minutes. But hopefully this won't take too long, and then we'll move on into the weekend and try something. Well, we'll expand on this as we move on into next week. But today we're going to talk about covariance and correlation. And to kind of give you a, gentle introduction to the topic, I want to show you a few videos, or actually just some random silliness. I've got this note here, by the way, before I forget it, that before long we'll talk about linear regression as well. We'll save that for next week and beyond. But before we get into all that, let's take a couple moments to check out some random silliness from the internet. So in case you're interested, when I was discussing signal detection theory, I talked at some length about perceiving signal within some noise, and I gave you even some actual audio stimuli that were structured in that fashion. And that's not just me just making stuff up on the fly. That's a kind of typical paradigm or analogy to use for signal detection theory, so much so that it even became the name of a book, a kind of a popular statistics book by this writer named Nate Silver, who you may have heard of. He became initially famous because of his work on baseball statistics, which is something I love to work on as well. And then that transferred over into him predicting the outcomes of presidential elections, and he did very well with that up until Trump won, which he didn't exactly predict, although it was still considered a possibility in his model. But anyways, but as of 2015, before Trump won, he was still considered like the king of online statistics. And it's kind of funny because I got married in 2015, and when I got married, I got this book that he wrote from more than one person. There's only one left in stock. Oh no. But I've got two in my library. It's called The Signal and the Noise, Why So Many Predictions Fail But Some Don't. And if you're curious, you can always check that out as kind of a more broadly appealing text on statistics than perhaps your textbook is. So I'll just point that out there in case you would like to check it out. Another thing, which is I think maybe more broadly appealing than math, is that there is a series of videos called Dancing Statistics, which I discovered a few years ago, and thankfully they're still up, because they're mildly entertaining. So this was put together by the British Psychological Society, and there's a series, I think there's 4 of them, yes. So the first one talks about explaining the statistical concept of sampling and standard error through dance, we know a little bit about this here. So this first one starts off with the blue dancer being the population. Here I am making a YouTube video where we watch other YouTube videos, but what are you going to do? So we're going to start out with the population, and then we're going to sample on the basis of that. So you guys should have a sense of what's going to happen here. This guy will make a rectangle with his arms, and then everybody else who's copying him will make almost the same rectangle in different ways. So the sample won't totally reflect what the population shape is, but yeah, hopefully you get it. If you take enough samples, you get a good picture of what the original population should kind of look like. And I think this is the one, not that one. I want to talk about correlation today. We'll take a look at this one because it kind of gives you a sense of where we're headed with this, just to kind of set the tone for everything. All right, so in this dance, the red dancers are one variable and the black dancers are another variable. Look at the first dance. What do you notice about the two variables? Okay, let's take a pause. Right, and lo and behold, our black and red variables, or our black and red dancers, are correlated with one another. They're kind of doing the same thing. And I think they have an example here eventually where they stop being, they talk about some things we're going to talk about today. I have a link to this video up on the course webpage, so you can check that out if you want. If you want to actually watch the whole thing. They're not that long. They're only about 5 minutes each, which is more than I can say for this series of lectures I'm making. The other thing I'll point out is that there is actually kind of a similar contest for some reason where people create an interpretive dance for their dissertation research, which is kind of amazing, because if you actually have gone through the process of working on a dissertation and finishing it, you know that it is very difficult to get through the whole thing. And on top of that, these people create their own dances based on their dissertations. So, wow. The one that won this year, if you can believe it, is about COVID-19. And yeah, they do quite a good job. They deserve to win, I would say. At least this one did. I will turn off the music. But this one's pretty amazing because she does a variety of different dances. She's got the ballet on the beach here. And then she's got whatever this is inside the room with funky lights. And then all sorts of like cool transitions between the two. Yeah, so this is describing, I guess, what proteins do or viruses do. And then she rocks out in the woods, because why not? I think this is from Oregon, so you got to do something when you live in the Oregon woods. The one from 2019 I thought was useful for what we're going to talk about today as well. It's about early life social experiences shaping social avoidance in larval fish. And the point is that social animals move in a coordinated way. So look at that. We saw coordinated or correlated dance movements before. We're seeing them again. These are humans and these are the birds, even though they're both humans, but they're pretending to be birds and ants as well. So yeah, you can check this out as well. Those are fun, and if you put one together for your own dissertation, I would like to see it for sure. But in the meantime, enough fun stuff. We're here to do business. So back to the big picture. Let's talk about why are we using these tests and learning these statistical methods. What's the point of this all? And if you remember, way back at the beginning of the semester, we came up with a series of answers about what we're trying to accomplish overall by doing statistics. And so one of the goals is data reduction, and that's the first one we tackled, basically looking at things like, different distribution shapes, or, 5-number summaries, talking about the means and the medians of distributions, that sort of thing. We have since learned how to do hypothesis testing and how to draw inferences from the results of hypothesis tests. Talked about that at great length, and we'll talk about it some more as we go, but hopefully you have the basic concept down by now. And what we kind of want to move on to now is looking for relationships or patterns in the data that might not be immediately obvious, but where we don't start off with a specific hypothesis, but we just kind of want to be open to what the data is telling us. And that's where looking at things like correlations can come in handy. So for this last one, though, I'm going to start off with a sort of moral before we get too far ahead of ourselves. And this is a kind of truism that you've probably heard before in other contexts in life, but you should still always keep in mind. And that is that correlation is not causation. So sometimes things can be connected with each other, but that doesn't necessarily mean that there's a causational relationship between one and the other. Yeah, if you want to think about that in terms of the dancing, you can go ahead and do that. But more generally speaking, like if you suspect ever that there's a change in one variable that might cause a change in another, then you have to set up and run a controlled study in which you change that independent variable and see what effect it has on the dependent variable. Yeah, I'm just trying to think. There used to be a funny kind of correlation that I used to talk about involving pirates, and I can't remember what it was, but it wasn't actually a correlation because it was sort of like pirates go down and something else comes up or whatever. But it's easy to find connections in the world. Like I've said before many times, our minds are kind of tuned into finding general patterns out there in existence. And that doesn't necessarily mean that we're actually perceiving the truth about any connections there. It's easy for us to kind of see that face in the clouds, even if it's not, actually a face, or the clouds didn't intend for there to be a face there. Likewise, it's easier for us to see that there might be a connection between two variables, but the scientific way to kind of figure out whether or not there really is a connection is to do this sort of thing, run a controlled study in which you change one variable and then see whether it has an effect on the other variable that you think might be connected to it. And I'm using terminology here like independent variable and dependent variable. I want to come back around to that again, but we're going to be talking about these sorts of things quite a bit as we go forward in this class. But an independent variable, it's kind of funny in this context because I'm saying this is the thing you could possibly change. Like, let's change like the, looking at two different genders of speakers, or maybe two different localities where we're finding speakers of English, that sort of thing. And we'll consider that the independent variable. And the dependent variable usually is the thing that we measure. Like in this class, we've done a lot of measuring of VOT and F0 and formant values, that sort of thing. We look at like how those dependent variables, those measures, depend on sort of those other underlying variables that we can have control over. So it's a bit funny to say that the one we control is the independent variable, but the relationship we're normally looking for is whether that dependent variable depends on the independent variable or not. And when you run a study like this, that's where, say, running a paired t-test might come in handy. For instance, if you look at just something silly like the difference in the weather between Calgary and Toronto, you can sort of just change that one variable, the location, and your dependent measure there would be like the temperature or whatever, and you can see how that measure depends on the location where the weather is happening. I'm just thinking about this because it's just such a wonderful, beautiful day out here. It's October 21st, if you can believe it, 2021, and we have the nicest fall weather ever. So I'm not going to pass it up without at least giving a nod and say, thank you, weather. This is a nice day. Anyways, this is also where we can start to get a little practical about what we're doing, because one of the big questions, so one big question that students often ask me if they're trying to run an experiment is like, how many subjects should I run in my experiment? And we've kind of addressed that question as best as we are able. But another question I often get is like, what test should I run for my data? And there's a lot of different possible answers to that. And it also kind of depends on how you set up your study. But we can think about it in terms of what the variables look like that we're looking for a connection between. So we have already kind of talked about t-tests at some length. And remember, what t-tests are basically testing is whether or not there's a difference between the means of two samples, or also between a mean and a hypothesized mean in a one-sample t-test case. But since we're dealing with means, that means that our dependent measure is gradient, or quantitative, if you will. And then our independent variables are going to be categorical, right? So like looking at like speakers from Calgary versus Edmonton, or, male speakers versus female speakers, or L1 speakers versus L2 speakers, that sort of thing would be our independent variable. We just have two different groups. And then the dependent measure is something that varies quantitatively rather than qualitatively. If you have a different sort of connection, or a different sort of possible connection, where your dependent measure is still gradient, something you can measure quantitatively, and your independent variables are also gradient, then you can run something called a regression analysis. And that's kind of what we're building up to now as we move through covariance and correlation to get there. But this is where, I think I've done a little bit of this in setting up the data frames for this class. But say if you want to look at how F0 depends not on, say, male versus female speakers, but say just on the height of the speaker. The height of a speaker is a gradient measure, and the dependent measure is still F0, so that's gradient as well. And when we run a regression analysis, we're trying to figure out if there's a meaningful connection between the two. Okay, enough talking. How do we actually do this? Enough preamble, I guess I could say, because I'm still going to keep talking. But I want to start this sort of line of analysis by reminding ourselves of how lines work. Thinking a lot about lines here. So this is going to be a review from a lecture earlier on in the semester. And normally I ask these questions in class to give people confidence that they remember this stuff, or can dig it out of their memories at least to some extent. So I would normally ask, what's the equation for a line? Maybe you've already answered that in your head by now, but the equation I'm going to go with for now is y equals mx plus b. And this is how it was normally expressed when I was first learning algebra way back when. And you can think about it not in terms of like these random m and b variables, but in terms of slope and intercept, right? So m is the slope of the line, which means it's a measure of the change in y divided by the change in x. And sometimes this is expressed as delta y over delta x. And sometimes if you're just a teenager learning algebra for the first time, they talk about it as rise over run. So that's all I'm going to say about that, other than the fact that we're going to be coming back to this equation quite a bit as we go through the linear regression, as we develop our understanding of linear regression. So try to keep this in mind, and also try to keep in mind that b is the intercept of a line, which is the value of y when x equals 0. So if x equals 0, then you multiply by the slope, but 0 times whatever is going to be 0. So you just wind up with y equals b, which is the intercept, right? And we saw some graphical examples of what that looks like, so we don't need to go through all that again. You can review those notes if you want to, but I'm just bringing this back into your mind because it's going to become important as we move forward. I've also had this little note down here that remember that 2 points make a line. That's all you need. So if you have point 1 where you have x sub 1 and y sub 1, and then you have point 2 which has like x sub 2 and y sub 2. If you connect those two, you're going to connect them with a line, right? And you can come up with an equation for that line that looks a lot like this, or looks exactly like this, in fact, with a slope and an intercept. And I'm not going to do all that again, just try to remember it. Okay, so the point I want to make to tie this back into what I was talking about earlier is that when you're looking at a linear equation like y equals mx plus b, then x is the independent variable and y is going to be the dependent variable. So the reason that y is the dependent variable is that its value will depend on the value of x. And of course, this being algebra, we could always turn this back on its head and express x in terms of y. And then it would, look like something else. But in that case, normally we'd be thinking of it kind of in the same way with just different labels, right? There's going to be one variable in here, and we're going to try to express its value on the basis of some other variable. So the dependent variable is going to have a value that we're going to try to express on the basis of the independent variable's value. I've also got a question here, which is also designed to sort of boost your confidence, because I've asked this question multiple times at this point. I don't know how many times you've answered it in your bedroom or wherever you're watching these things, but what's the equation for variance? And I think this will be the last time I ask about it for now, but variance is the sum of squares divided by the degrees of freedom, and this is what that looks like here in mathematical notation. This is the sum of squared differences here on the top of the fraction, and the degrees of freedom here down on the bottom. And just remember that variance is expressed as sigma squared, whereas sigma just by itself is the standard deviation. And we'll be seeing those guys again here pretty soon. All right, enough review. Let's talk about some new stuff. So we're going to be considering a situation in which there are two independent variables, each of which is gradient. And like I said, we're going to try to figure out whether or not there's a connection between them. So there might be a connection, and what we want to find out is exactly how much of a connection there is. We want to quantify it. Okay, so how we start doing this is we're going to basically index both variables and then compare both sets of variables one by one to see if both sets change in the same direction each time. So what I mean by the indexing, this is hopefully going to be familiar from when we talked about the summation notation, but say you have the set of x variables, so you have x sub 1, x sub 2, x sub 3, so on and so forth. And then on the other hand, you have y, like y sub 1, y sub 2, y sub 3, so on and so forth. And we're looking at those connections between x sub 1 and y sub 1, x sub 2 and y sub 2, so on and so forth, all the way down the line. So Keith Johnson, my former advisor, tries to do this in a sort of very not fine-grained way, I guess very granular way, in his textbook by looking at the F1 and F2 of 5 different point vowels. So E, A, A, O, U. And this is sort of like that normalization paradigm that we apply to our own format values a while back, but he does it in, like I said, a very granular way. So instead of talking about the z-scores of the individual format values here, he looks at whether the F1 of each vowel is higher or lower than its corresponding gender mean. So in this case, you get a group of male speakers producing these vowels and a group of female speakers producing these vowels, and you calculate an overall mean for male F1 and an overall mean for female F1, and then you look at each vowel and you say, is it higher or lower than that mean? And he comes up with what he calls a contingency table of the data, where we're looking at whether there's a connection between female F1 and male F1. So let's say for female F1, we have a set of vowels that have an F1 above the female mean. Normally you get that for the vowel ah, and you might get it for the mid vowels like O and A, but you might not. And then he also looks at, sets aside a group of vowels that have a F1 for female speakers that is below the mean F1 for female speakers. So E and U will typically have a F1 value that's lower than the mean. So for these 12 vowels, 12 female vowels that have an F1 below the female mean, how many of them also have a F1 for male speakers that is below the male mean? And it turns out that 12 of them for the males also are below the male mean, and then one of them is above the male mean. So there's just one exception here. And then for the aboves, all 6 vowels that the females produced, well, actually, I guess it's the other way around. Sorry. These are, sorry, I misspoke. So these are the 6 vowels that are both above the female F1 for female speakers and then above the male F1 mean for male speakers. And then there's one exception, which is above the female F1 mean for female speakers and then below the male F1 mean for the male speakers. And for the belows, there's a connection between the two. So what we see here is that there is a connection. If it's an F1 that's higher than the mean for females, it's probably going to be higher than the mean for males as well. And same thing for the below vowel F1 values, but we get this one exception here, which means that it's not a perfect correlation between the two. So we're getting something of a linear relationship here. It's almost a totally predictive relationship, but not quite. However, we want to dig into the data more deeply. And what Keith says in his textbook, which is a very apt observation, is that it would be much better to explore the relationship of these two variables without throwing out the information. So what we're throwing out here is, say, the specific F1 values for both the male and the female speakers, and we're tossing it and just saying, kind of converting it into a categorical measure of above or below the mean F1. We could get more out of that, right? So like I said, maybe O and A are going to be below your mean F1 measures, whether you're a male or female speaker, but will probably definitely have, sorry, I'm screwing everything up here. O and A might be below your mean F1 measures for both male and female speakers, but E and U will probably be even lower in terms of F1 than the O and A. And we're counting them both as the same. So like maybe O, definitely U, and if they're below that mean, we're just counting them as below. But we're losing that information about the differences between O and U in that particular case. Hopefully I haven't talked over myself here too much, but what we're going to do to try to sort of solve that problem is we're going to look at gradient variables rather than those categorical variables in that contingency table. So to do this, we're going to come up with a measure called covariance, and it's going to start with the deviations from the mean of each variable and then multiply them together. So before, if we were thinking about like looking at mean F1, and we know we have say O and A kind of around the mean, and then U and E have a really low F1 measure. A has a really high F1 measure. What we're going to do is calculate the actual distance of that F1 measure from the mean. We're not just going to say above and below. We're going to say, oh, maybe it's 200 hertz, or maybe it's 50 hertz below. So 200 hertz above, 50 hertz below, whatever it is, we're going to keep that numerical information and then see if there's a connection here between our two groups of speakers, like males and females, in terms of the actual numbers we're getting rather than whether just above or below. So to do that, we're going to calculate a quantity known as the sum of the product of deviations. So to give you an example here, all don't know if I can just pop this out here. So let's say like if our mean F1 for the men was, say, 500 hertz, we might get a specific value of F1 for which is 750. And let's say our mean F1 value for the women was 600, and we might get something like 850 for their F1 value for like an that sort of thing. So we're going to look at these differences. It turns out they're the same in both cases. So like 250 for both the male and the female speakers, and then we'd multiply those together. So 250 times 250, whatever that happens to be. I don't think I can do that on top of my head. I think it's like 62,500, something like that. It doesn't matter. All we're doing is knowingly gonna calculate the differences and then multiply them together, and we can let R worry about the details. We're gonna define covariance as the sum of the product of these deviations, this bit here, divided by the degrees of freedom. And to give you a specific example of how to define this, sample covariance, the degrees of freedom will be n minus 1. So if we have like 10 vowels in each set, then n equals 10, and we subtract 1 from that to get 9 because the mean is getting involved here again. And then we just run the numbers to get a value of covariance out of that. Okay, I want to walk through the properties of this equation together a little bit. Sorry. Got to pick up my trash before I walk away. But let's say if we have positive values of deviation from the mean, then if we have positive values for both x and y, then those values will reinforce each other. Negatives will also reinforce each other, but opposite signs will cancel each other out. And to kind of give you an example of what I mean by that, this would probably be another case where it would be useful to be on the board. So before we were looking at like 700 minus 500 times something like 850 minus 600. Let's say this is just what we get for some sample F1 values for for a given pair of speakers. So if you do this, they kind of reinforce each other. Like I said, it's 250 times 250. That will be a very big number. But let's say instead of 850 for the female speakers, I had 350. So in this case, what I wind up getting is 250 times negative 250. Maybe I'll put that over here. That would equal this times that. And that will wind up being a very large negative number, I think negative 62,500. So the sign matters in this particular case. We're still getting information about sort of the quantity, like how big these deviations are, but the sign will push us in one direction or the other. And also if we have the opposite situation, so this might be like our F1 values for E perhaps, or U. If we have negative 250 times negative 250, then we wind up with a product here of positive 62,500. That's just the way signs work in multiplication, right? So that's all I'm saying on that next page. Positives reinforce each other, or sort of linked positives reinforce each other. Linked negatives reinforce each other, but opposite signs cancel each other out. This is kind of the one that makes it interesting right there. What we want to see is sort of deviations from the mean moving in the same direction on either sides, on both sides of this sort of two-set comparison that we're looking at. But if they move in opposite directions, then they're not correlated with each other. I also have this point about big matches really reinforcing each other, big deviations from the means. So that's pretty easy to understand, I think. 250 times 250 will give you a much bigger number than like 25 times 25, so on and so forth. I also have this question here, which you have already seen the answer to, about what are the upper and lower bounds on this measure, and the answer is none. So as you know, numbers can be as big or as small as they want to, because we've got stretching out to infinity on either side, and that's as big or as small as covariance can be as well. So sorry for giving away the game on that, but that's basically the answer to keep in mind for covariance. And this is how it's defined for samples up here. So to give our measure of covariance meaningful limits, if we don't have to want to worry about everything from negative infinity to infinity, then we can basically normalize covariance with respect to the product of the standard deviations of both variables. So this is just a quantity which we're going to throw out here and say this is how we define it. But it turns out to be a pretty amazing measure because it can be expressed in a wild variety of different ways, all of which are useful in some form or another. But this measure is called R, or the correlation coefficient. And for now, we'll define it as the covariance of x and y divided by the standard deviation of x times the standard deviation of y. And like I said, the goal in creating this measure is to kind of give limits to the covariance we observe in our data. So it's worth it to think about what those limits might be. So first, before we play around with this, because I'm just like plopping this out there on you and saying this is how we're going to kind of normalize things, I want to convert it into at least one new form so you can kind of see a little bit better what's going on inside this quantity. I'm just not going to have space enough to do so until I move on to the next slide. So again, be thankful that I'm not scrawling this stuff out on the board, because it would be really hard for you to write down because you couldn't read my handwriting. So we're just going to read it off the slide here, which is boring, but still easier than normal. So we're starting off with R defined as this, covariance divided by the standard deviation of x times standard deviation of y. In this second step, what I've done is just plug in the definitions of both of these quantities. So covariance is up here, and we've got this product of deviations over here divided by the degrees of freedom. And then for both the standard deviations of x and y, we're going back to that definition of variance we've talked about at great length many times over. So we've got the product of the sum of squared differences in the numerator of the equation, and we're dividing it by the degrees of freedom on the bottom. And to get the standard deviation, we take the square root of that whole thing. Okay, so how can we simplify this, if at all? What I'm going to do is recognize that on the bottom of both these equations, we can basically get the square root of n minus 1, but we're multiplying those by each other. So we can kind of factor the n minus 1 out of that and just say we have the square root of the product of sum of squares of x times the product of sum of squares of y, divided, the whole thing divided by n minus 1. And we have an n minus 1 up here as well, so we can simplify that further by just eliminating the n minus 1 part of it, and then we get r defined this way, which is the deviation in x times deviation in y, sum all that up, divided by the square root of the summed deviations of x squared times the summed deviations of y squared. I'm going to stop there for now, because I think that's going to be enough for us to kind of get a sense of how R works, or at least what its limits are. Yeah, I can probably make 2 million puns about R and the verb are, but I should not even get started on that because none of them will be funny. So we'll just leave this equation as it is, and we'll keep working with it as we go forward. And for the moment, I want to think about its properties, and namely its upper and lower limits. So here's bad dad joke, because I've put an Eagles song as the title to this slide, which is, I'm sure, a no-no in most circles. But here's our definition of R. What are its upper and lower limits? I'll let you think about that for a second, keeping in mind that covariance had no upper and lower limits in any meaningful way. Usually in class, if we sit and think about this long enough, whether it takes 1 minute or 5 or more, then people can figure it out. Hopefully you can see what we get in sort of the limiting cases are situations where the sort of linked deviations wind up being the same. So if x sub I minus x bar always equals y sub I minus y bar for every single data point in our two sets of data, then what we get there is R equals 1. So basically what we'll wind up getting there is kind of squaring these deviations on the top of this fraction, and then because we're squaring and then taking the square roots here, well, put it this way. Let's say x sub I minus x bar is always 3, and y sub I minus y bar is always 3 as well. This times this will be 3 times 3, or 9. And then down here, you're sort of squaring 3. That gives you 9. And then down here, you're squaring 3 again. That gives you 9. 9 times 9 is 81. But then you take the square root of it, and you get 9. So you wind up with 9 divided by 9. And I apologize for not writing this out, but again, you don't want to read my handwriting. So in the case where these two are equal to each other, we're always going to get a value of r equals 1. That's a perfect correlation between the two variables. And then maybe you can see that if you just switch the sign of one of those and say have x sub I minus x bar equals the opposite of y sub I minus y bar for all I, then r is going to be equal to -1. So all you're doing there is winding up with a difference at the top here, because whatever we do down here on the bottom is going to be positive. That's how we can kind of normalize by that factor, because we're squaring and then taking the square root. We'll always wind up with a positive number down here. But up here, this can vary between positive and negative numbers. That's sort of something we keep preserved in the calculation. Is not only the quantity of the deviation from the mean, but also the sign of the deviation from the mean. And if these two are always the opposite values of each other, then r is equal to -1. And those are the limits. The highest value you can get for r is 1. The lowest value you can get for r is -1. And it doesn't go from negative infinity to infinity, so you don't have to worry about anything beyond that, which is kind of cool. Couple crucial points. Number one, the match between these two deviations determines the sign of the correlation. But again, you're summing up over a series of values, so you can get greater or lesser sums for that reason, but the sign will determine which direction you go in any particular step. And I have this point about, we'll stop there to keep it short and sweet this time, which I definitely want to do. But at this point, people will usually ask whether there's some meaning to r equaling 0. And I'll say yes, there is, but it's complicated to get to, but it does crop up in particular context in a meaningful way. I will just say that if r equals 1, then you have a perfect correlation between your two variables, kind of like x and y are always doing the same thing as each other. If you have r equals -1, then you have the sort of most perfect negative correlation you can get between two variables, where x and y are always doing the opposite things of each other. And then in the weird case we have r equals 0, there's no correlation. So there's no connection between what x and y are doing with each other at all. So that's that special case, but we'll find out how to get there mathematically in the next couple of lectures. For now, just think of perfect correlation being perfect correlation being r equal to 1, and then a perfectly opposite correlation being r equal to -1. And I'm going to stop there before I misspeak any further, because like I said, I want to keep this one short. So I will see you guys next week for the dramatic continuation of our adventurous exploration of the quantity of r. See ya.